So today, neutralization is actually a process in which we could take either a very strong acid or a very strong base, or in some cases both of those, and neutralize it. Now, what do you think about when you hear the word neutralize? Okay, no charge. What else? Nothing? Like think about nothing? Or all right, in terms of, let's say, pH. And again, we haven't formally talked about pH in here, but if you hear that a solution is neutral, like water is neutral, what pH are you thinking about? 7, yeah. So in the middle of the scale. 0 is really nasty. That's a really high concentration. So I could take like a really strong acid or a really highly concentrated acid, pour it on my arm, you'd start to see my arm melt. It wouldn't be very pretty. I could take a very strong base to the other arm and do the same thing and just look like I'm not a very smart guy. But if I mix those two things together, the acid and the base, I'm actually going to produce salt water. And if I use, say, let's get some room here, right? Let's say that I had, say, sodium hydroxide and hydrochloric acid. These are really nasty things by themselves. And if I put them together, what am I going to form? Does anybody remember? NaCl, because it's a double replacement reaction, so we're going to switch. And water. So essentially we're making seawater in this case. So I can mix those two acids together and technically drink it and not be hurt. Now I wouldn't want to drink it because I'm not a big fan of seawater. I mean, when I go swimming in the ocean, yeah, I get quite a bit of it. Drink quite a bit of it, but God knows what's in it. You always drink it before you put your feet in? You chug? That's smart. I like that. That's good stuff. But the water is what's neutralizing. So we're taking out those hydrogen ions in the acid and those hydroxide ions. And those are the things that actually make the acid or the base pretty nasty by themselves. But we put them together, and what do we make? Water. Look at that. So yeah, HOH makes water, which is kind of cool. Okay? And then salt is just the byproduct. Now, most of the time for these types of reactions, the salt is soluble, which means it dissociates and you don't even see it. But there are some cases where I could make an insoluble salt. What does that mean again? It won't dissolve, or it forms a precipitate. Very nice, a PPT. Okay, so that could happen. Don't freak out if it does. We actually did it last topic when we had the neutralization reactions. You don't realize it, but we were doing a little foreshadowing back in the last chapter. Defining neutralization. Defining it simply means that we're removing hydrogen or hydroxide and that we're moving toward a neutral pH in that case. So everything that you learned in junior high, middle school, whatever, hopefully it's still true. Okay. Complete neutralization, in most cases, what we're dealing with is a monoprotic acid. Monoprotic means that you just have one hydrogen, but in some cases you could have a polyprotic, which means what? More than one. There you go. So, like sulfuric acid is a great example. If I have sulfuric acid and I place it in solution, it's going to break one hydrogen off at a time. Oh, sorry. That's a lie. So it'll form that, and then what's going to happen is we're going to take our HSO4 and bisulfate, and we'll break another hydrogen off and make sulfate. So what happens is we've got these two hydrogen ions in solution. So I could have 1 mole of sulfuric acid and actually get double the concentration of our hydrogen. If we were talking about a Van Hoff factor in this case, which we're not, what would the Van Hoff factor be for the sulfate in terms of hydrogen? 2. So we'll get 2 hydrogens for that. Now, what's nice is if we are reacting this with the strong base and we have this hydroxide, this kind of coming around here, it'll actually jump on that hydrogen and make a water molecule. If we have another one, it'll jump on that hydrogen and make another water molecule, which will neutralize it. Okay? So it's all about the hydroxides jumping on the hydrogen. As long as we're having fun, it's okay. A titration is a process, a lab procedure that we're actually going to do in a couple weeks. And it deals with a burette, which is a really nice piece of equipment. It's expensive. It's a glass tube that has like 1/10 of a milliliter markings on it. I have a video that I just linked today that I made while I was at Avon. And what it does is it typically you'll put a strong base. Actually, let me show you the video here and I'll describe it as I'm going through. Oh, sorry, you didn't need to see that. All right, so here, okay, so let me pause the video. So what I've got is, and it's really hard to see because I was trying to make it dark so you could see what was going on here. Here's a magnetic stir, and a magnetic stir looks like one of these things, and it's on a stirring plate, which is rotating it, mixing it up. And I put a strong acid in here with some phenolphthalein, which is an indicator. And what this indicator does, it indicates when you're at a desired pH. The desired pH that I'm looking for here is 7. So, and what I have here, I'm starting to add the base to the solution. There's a pH meter that's actually located inside of this, and it's tracking the pH as I add the base to it. I'm going to fast forward a little bit here. Okay. What's that? It is the indicator. So move up a little bit here. And as we start to add some more of the base, you may notice that you're starting to see the solution starting to turn pink. Now notice that it's not all pink or hot pink there, and I've got another view here in a second, until it becomes a pH of 7. So, and as that happens, notice how the pH just spikes. In AP chemistry, we do some titrations, and you'll get, hopefully I think we have some pH meters in here. We'll get to see that take place as well on your computer. All right, so let me fast forward even further. Okay. So here I have another view where I'm actually, you can't see the burette, but I have the acid in here and I'm adding the base. And as I add the base dropwise, you can start to see the solution change. If I start to add it, there it is. And as we get closer to our neutralization, then that pink stays in a little bit longer. And you'll see this in a couple of weeks when we do the lab here. Actually, move it up, get closer. Okay. So you can see that, and it'll go away because, shoot, let's go back. Oh, there it goes away. Okay, so it went away. So that means that as it stays pink longer, we're getting much, much closer to the desired pH. I think one more drop and it's going to stay pink here if I would ever do it. There we go. And so right now, we are at our desired pH. And that one drop actually changed the pH from like about 5.5 to 9. That one drop changed it that much. And it's a really light pink. I think it's going to stay that way. I added another one deck on it. But now we're at our equivalence point. Any extra base that I add to that is only going to make this a little bit darker or stay the same. Now here I've got my graduated cylinder, and it has the residue of the acid that I poured into that. I'm going to take some distilled water and rinse that out. What do you think is going to happen when I pour that in? It should go clear? Yeah, so there's enough of those hydrogen ions in there that when I add it to it, it will do it. Go back to being clear. Okay. And then you can start that process all over again. So this is a titration, and it's a pretty cool process. I think when I was at Butler, we probably did about 20 of these, and it started to get boring after a while. But when you first see it, it's like, whoa, this is pretty neat. But this is what helps us to measure the pH, to determine what the concentration is or how much of a volume is needed, etc. There's a lot of things that we can do with this. All right, so go away. All right, so, and I had on there the indicator. We use an indicator, and there are hundreds of different indicators that exist. And each indicator is very specific for a pH. So if I wanted to find what the neutralization, we could have a different reaction where where we get to the equivalence point, or the moles of the acid equal to the moles of the base is at 3, I would have a different indicator. But this is a great example for basic chemistry. The equation that you see at the bottom there is what you'll be using for the homework tonight. And it's VA times MA is equal to VB times MB. Now, VA represents the volume of the acid. MA represents the molarity of the acid. And then we have the volume of the base times the molarity of the base. This looks a little bit like P1V1 equals P2V2. You'll get 3 of the 4 variables. You just have to solve for the unknown. Now, what's really great about this is if the volume's in milliliters, you can leave it in milliliters. Now, if I have one in milliliters and one in liters, then we got to change one of the two. Okay. All right. Let's do a practice problem. Okay. Now, the hardest part of these types of problems is determining who's the acid and who is the base. So when looking at this, number 7 says when 42.5 milliliters of a 1.03 molar NaOH, so NaOH, is that an acid or a base? How do you know it's a base? Has the OH, also it ends with hydrogen. So this is our molarity of our base, and there's the volume of our base. Is added to 50 milliliters of vinegar, a solution of acetic acid. So what does that 50 milliliters represent? VA, the volume of the acid, very good. And then it says that the phenolphthalein in the solution just turned pink. That doesn't help us do anything, it just tells us the word neutralization. It wants us to calculate the concentration of our acetic acid, which is our molarity. Now remember, when you talk about concentration, so it's equal to the molarity, which is equal to moles over liters. This is just a review, you don't have to write that down. So when you hear me use the term concentration, I'm not telling you to focus, I'm telling you about molarity. Yeah.
How do you know which one is like B and which one's A?
Okay, so like at the beginning here, let me color. It says when 42.5 milliliters of a 1.03 molar solution of sodium hydroxide, that information goes with the base. So the hardest part is asking yourself, what is that? Is that an acid or a base? Okay. And then the second part says is added to 50 milliliters of vinegar, which says it's acetic acid. So there's your other component. So that's why I always write the variables above it, just to keep me from doing something dumb later on. Okay. So looking at the equation that we're going to use. So MA, VA, MB, VB. And which variable are we solving for here? MA. So I should have put a question mark on there, sorry. So we're looking for MA, so that means that we know everybody, or put all the knowns to one side. So our equation now looks like this. MA equals MB, VB over VA. And then from there, plug and check. Okay. So MB 1.03. And do show units on this. Times 42.5. And 50 mils. So MA is equal to something less than 1. I know that. 0.875. I like that. Okay, I could do that too. Okay, so again, the hardest part of this type of question is identifying what these are, the variable-wise. Okay. Try number 8 on your own. Don't peek up here. Oh, yeah, I'm sorry. Add 7.28 molarity. My bad.
I only have 2 numbers.
Yeah, tack that on. That is kind of necessary to answer this question. My bad. So 67 milliliters of a 7.28. Yeah. first hour told me that. I was like, oh yeah. Sorry about that. You might get a number. What is it?
1991.28.
How's that? Okay. So the homework is the 4.